the last talk with Bert, did everyone hear him okay? Great. Okay. Well, it's an honor to be here. I think we have a really well-structured program, and the reason is because of that man there, Brian Vincent. So he did all the organization, he recruited the speakers, he did all that. It's a tremendous amount of work. Brian was my master's student and my PhD student. He's always been organized, meticulous. It's just how he is. And I need someone like that. Yeah, you see, he's pointing at me. Next to Brian in the back, the other reason I'm still alive is my wife is sitting there. See her in the back? There she is. My wife. She's Japanese, and so she always says, yeah, Japanese quality. So it's true. The Japanese quality of seafood in particular is the highest possible. So I didn't forget my wife. This is really important. I've been married 51 years. That's why. How did she know that was me for 51 years? Okay. Recently, in the press, there was a high-profile failure in Auburn, New York, called local coho, and it was coho salmon. I think approximately $17 million went into it. It failed as a dispersal. Actually, in the newsletter for the RAS, which you all have, there's a little bit about that farm for sale. And so a very esteemed person in the industry asked me, like, well, why did they fail? And I said, they didn't follow mass balance rules. So what's the talk today? Mass balances. So I've given talks hundreds of times. I still get nervous, so I apologize if you're nervous, because I'm so excited. Okay. Mass balance run rates. The talk is about an hour, so we can't do that. So because there's 58 slides, you can't do that in an hour. So I'm going to go through the first half of the slide, and there's an actual example that we won't cover, but it is in the presentation and it's available. And all these presentations, thanks to Marlon Greensword up here. Say hi, Marlon. Marlon is taping all these. He's one of the on the board of directors of the RAS, and all these are going to be available through our website. Yes, sir. If we're successful.
Oh, yeah.
Okay. So the yellow book actually had this equation at the bottom here. You see transport in of X plus production of X equals transport out of X. And I would I taught for a long time, and I say, okay, it's going to be a closed book test, but you can use the cover. Because it's all about that equation, folks. It's so simple. It's all about that equation. You know, transport in plus production of something equals going to be the production. I find the down button. Does that work? Great. Okay, so there's the equation. Transport in of X, and X could be like transport in of oxygen, it could be transport in of ammonia, it could be CO2. There's usually four things we look at in alphabetic order: ammonia, oxygen, ammonia, carbon dioxide, solids, carbon dioxide. It's hard to get it. Ammonia, carbon dioxide, oxygen, and solids. There we go. Those are the four. Everything else will be less defined in those four things. Okay, so the key here is then this flow diagram. And so just look at that a long time. And so engineers like to think of a control volume. That's the little dotted lines. And so then that says, okay, that's what we're going to focus on. And so things coming across the control volume line. Is there a pointer?
Yeah.
This black thing? Whoa. Yeah. Okay. So here's our control volume. So everything crossing this is the mass balance. Okay. So transport in. So we have something coming from the outside. Those are makeup water. If you had no makeup water, of course, that's zero. And then we have things leaving. So there's some discharge. And here's water that leaves and goes through some kind of a treatment device and comes back. but you don't see the treatment inside the control valve, right? So it's what's coming back in. So we have flow in plus the production of something equals the flow out of stuff, okay? So you set that up mathematically, and Q, is the flow term, this is the concentration term, and there it is mathematically. So typically, your makeup water is very small. So if you're doing rule of thumb, quick calculations, okay, you can just cross that off. So in fact, if you think about it, like as Bert was saying, what is the makeup percentage? Maybe it's like 10%. So, and what's our flow rate going around in circles? So 4 times. Let's just say it's once an hour to keep the math simple. Okay, or maybe twice an hour, right? So in 24 hours, that means that tank is going to turn over 48 times, right? Or let's round it up again to 50. Okay, 50. And if we're doing recirc, 10%. So put 50 in a percentage. 50 as a percentage is 5,000, right? 50, 500, 5,000. So 10% over 5,000, it's like you can just throw it away. Does that make sense? Even if it was 1 tank a day of throwaway, that's 100%, that's 100%, 1 is 100%. 50 is 5,000, right? That's still 50, it was 1/50th. So it's all about this, it's really all about this recirculating term going around in circles. Okay. So there's a unit balance. I won't bore you with that. There's our mass transport term. So I do a calculation for you. So as an example of like available oxygen coming back into the tank, Q times C. So let's do, English, 100 gallons per minute. We change that into liters off the pump, so we get times our concentration in, and what we say, okay, saturation, 9.8 degrees C. So that gives us 5.39 kilograms per day of oxygen. So, rule of thumb, right, is it for every kilogram of feed you feed, you need about a kilogram of oxygen. That's a rule of thumb, right? So to trick my students, I would say, I used to trick Ed Anderson as one of my students. I used to trick him easily all the time. And I'd say, so if I got 5.39 kilograms per day of oxygen, it takes 1 kilogram of feed per day. How many kilograms of feed could I do? And Ed would say, well, 5.39 kilograms. I say, wrong. Why is that wrong? Think. Why is that wrong? Because that would be if I took all of the oxygen out to 0. So you have to have some oxygen left over, right? So then the class quickly catches on. So we talk about available oxygen. So maybe a design value for the tank might be 5. So now you got your saturation coming back from the treatment system or whatever. And then we have 2.67, for example. So this is one of the tricky parts. What do you set as your value for the treatment system to achieve to bring it back into the tank? And so I'm an engineer, and so I'm kind of biased towards that. So if I would talk to my, no offense to the biologists, how many engineers are in the room? Have any degrees in engineering? See, we're kind of the minority, right? It's kind of a funny thing, right? So if we talk to our biology friends, they say, well, what do you want? What do you want for the oxygen? And the biologist goes like, well, saturation, or something close to saturation. I go, well, we could do that, but I may not stay in business very long because it's going to cost you too much. So maybe we need to talk about economic optimal. That's going to first be below saturation. Okay. Anyway, have those again. So this is your job, as the designer or the consultant, to come up with these values that you're going to select. And there's a warm water species, tilapia, and cold water species, some are. These are kind of typical numbers that you might choose in this class. In this class, everybody's looking like that. So now we have to